So good afternoon to all of you. Today what we are going to see is we are going to talk a little bit about stability, and then we are going to see how to introduce an instability and make oscillators out of circuits. Okay. So like we talked about feedback in the previous class. So essentially what we were doing, we were taking a positive signal, and then we were taking a portion of the output signal, and we are subtracting these two signals. So if you see, as long as there is this signal when it comes here, as long as it is not making an 180-degree phase shift, okay. So you will find these two signals, and the difference of the signal will be amplified, and then there is no so it would work fine without getting into saturation or things like that. Okay, some two examples are given here where we have taken a capacitor here. This example we saw where from the output. So although you might say these two signals are added out here, but then the signal at the output is inverted because of the transistor operation and the biasing out here. We know that for a common source amplifier, the gain is negative, right? It is 180-degree out of phase. So that this subtraction portion is taken care of already here. So that is why you can say that these two signals, they subtract from each other, and the different signal is fed to M1. Okay.
Sir, I have one question. This positive feedback. Why is that going to the negative terminal there in that amplifier?
Here, yeah, I'm coming to that. Again, we saw one more here where the output is here this is known as a positive feedback, where if at all in the feedback network, if the signal is getting inverted, okay, so if beta is such that this beta network is such that it is introducing an 180-degree phase shift, then you will find this is the signal, right, and this signal is inverted here. Like in the negative signal, the condition is that these two signals should subtract each other. Here what happens is, because of certain elements in the beta, the signal is getting inverted by 180 degrees. So now if you try to subtract these two, they get added up. So we essentially land up in a situation where this system is not stable. Not stable means you have some small signal, it will go, it will get inverted here. So this plus and minus, minus again they will get added, again it will get amplified, and eventually you will start getting a positive square wave out here. So it will break into oscillations. That's what. So that is known as positive feedback, which is not desirable. So this is another diagram which shows what happens when, if you start doing like this, then the circuit will no more work as a negative feedback network. Okay, so that is known as disturbing the stability of the circuit. So we should try and avoid that until and unless we want to operate it deliberately as an oscillator. Okay, so so we have to ensure. So now if you see, for the stability, we have a signal out here, you have an input signal, you have an open loop gain of the amplifier, and then you have a feedback. So we know this is the open loop gain. Now if you see here, if this alpha beta becomes -1, so we have a situation here, 1 minus 1 becomes 0, so infinity. So that means this will break into oscillation. So that situation of 1 plus alpha beta equal to 0 should be avoided. Otherwise, the circuits are not going to be stable.
So this is closed loop gain, right? You said open loop.
Yeah, this is closed. Okay. This is A is the open loop gain. This is the closed loop gain. So so this becomes infinite. Okay, so if the loop gain here becomes 0, so you have to be careful with the design. Okay, now let's just take a single pole response. Okay, that is, you have just a resistor and a capacitor. Now so V out will be given V in into this impedance. Okay, this is 1 by C omega, right? That can be written as minus j xc. Xc is nothing but 1 by C omega, right? So xc. So and then sum of these two impedances, which is R minus j xc. So we know that the resonant frequency is given by omega 0 is equal to 1 by RC. So the gain is minus XC by A, this. Now it can be also written as 1 plus an RJC omega, or if you write in this form, it will 1 plus J omega divided by omega 0. Okay. Now if you see here, this is the magnitude of the gain, 1 plus omega divided by omega 0, right? This is polar form. So if you take the magnitude, this will be the magnitude, and this will be the phase angle minus tan inverse omega by omega 0, right? And the gain in dB, the power gain will be written 20 log AB, right? So when we say half power gain, that means the power is half, or the amplitude will be 1 by root 2. So if I put 1 by root 2 out here, so it comes out to be minus 3 dB. That is from the mid band. When the gain goes to minus 3 dB, the power will be half of that. Now again further some analysis about this. So when the frequency is very very low here, if you see here, right, this is just an RC network. So omega out here is 0 out here, right? So the gain is around 1. Okay, that means this signal whatever is applied here, this capacitor will act like an open circuit. So whatever signal is applied here will be available here, right? So this is what? This is a low pass filter, right? If you have an RC like this. So for very low frequencies, as omega is much lesser than the resonant frequency, power gain is the voltage gain is 1, and power gain in dB is 0, and the phase is 0. Okay. Now here just please understand these 3 steps very carefully, because these are extremely important to understand the stability criteria. So for low frequencies, very low frequencies, okay, power gain is 0 dB. That is voltage gain is 1. So if I write 20 dB log 1 is what? 10 to the power of 0 is 1, right? So that is why this becomes 0. So power gain is 0. Phase is 0, because this is negligible, right? So omega is much lesser than omega 0. So this is tending to 0. So tan inverse 0 is 0 out here, right? So is this top line clear to all of you? This particular condition, these 3 conditions we need to look it very carefully, so that to understand. The top condition is okay. Yeah, okay. So now let's take a condition where omega is equal to omega 0. Omega 0 is nothing but 1 by RC. So if we put that value out here, right, this is same. So 1 plus 1 square will be 1 by root 2. So gain magnitude will be 1 by root 2. That means now A is 1 by root 2, power will be minus 3 dB in that case. That means the power has now reduced to half. Okay, minus 3 dB means half the power. Okay, understand that. So in dB scale, it is minus 3 dB. So in this particular circuit, when the frequency has reached 1 by omega is equal to 1 by RC, the power has become minus 3 dB. Initially it was 0. So 3 dB frequency power has been lost by the time the frequency has reached omega 0. What about phase? Okay. Now phase omega is equal to excuse me, omega 0. So if I put omega is equal to omega 0, this will become tan inverse minus of tan inverse 1 by root 2, which is 45 degree, minus 45 degree. Excuse me.
Sir, I have one question.
Yeah.
What is the difference between that omega and omega 0?
Omega is omega 0 is 1 by RC, whereas omega is variable. It can take 0 to infinity. So we are analyzing what happens to this circuit where the frequency
Omega is a frequency, right? Input
yes,
frequency.
2 pi f. Yes. So for various
so
frequencies.
yeah. So omega is you are saying we can vary that to any.
Yes.
But sir, why we are putting omega 0 as 1 by RC? What is the reason behind that?
Because that corresponds to a frequency where the power becomes half. Okay.
Okay. Okay. At 1 by RC, power becomes half. Okay.
Yes. So, at that place the phase becomes minus 45 degree. Okay, that is also important now for us from stability point of view. So, after that what happens? Okay, now if you see here, for every decade what happens? So, if I write this A equation, omega 0 divided by omega 1 square. Okay, now if I write the second equation here, where initially it is this should be 10 omega 1, sorry, so omega the frequency is increased to let me do it straight away.
Sir, that phi is what angle is that? The phi 45 degree, 90 degree.
That is the phase angle gain. Excuse me. So now from here to here, if I increase the frequency 10 times means I am increasing by one decade. So this will become 1 by 100, right? So 100 plus 1 I can approximate it to 100 only. So so this becomes an under root. So it becomes 10 AV. So by increasing the frequency, okay, so it will become it will be sorry, again there is an error out here.
Sir, one more question I have. Why we are calling that a single pole? Because I see in the next slide you are saying 3 pole. So why is this single pole?
Yeah, this is single pole. Yeah, I'll come to because there is only one RC out here. That is the reason I'm calling it as a single pole.
Okay.
Yeah. Okay. So when I'm increasing the frequency by 10, okay, by one decade, so you will find that gain is decreasing by 10. Okay. Now if I put in the gain equation, it is what is power 20 log AV. So the gain is decreasing by 10 out here, right? So again I did a lot of mistakes out here. So let me correct this. So this is gain is 1 by 10, right? So log of, if I put it right, so 1 by 10. So this will become minus 20 by dB.
Sir, in this AV1 and AV2, omega 0 should not be in the denominator.
Yeah, okay, yeah, correct. I made a mistake again there. Let me change that. Omega 1. This will be omega 0. Right? And this will become 10 omega 1, right? And this will become omega 0, and let omega 1.
We need to remove 10 also. Okay, anyway, sir, we understand that.
Which one? Here the bottom.
This one down. 10 moment.
Let me do it right now, because finally when I share the slides, it will become.
We are increasing bandwidth, right?
No, we are not doing anything. We are just analyzing the RC network. When I am increasing the frequency, okay, initially I was W1 at some frequency which is above RC, okay, above RC. I am talking about a condition about above RC, omega 1, and from there I am going again further increasing by one decade. What happens to the gain? So from this equation I can see that the gain will reduce for every increase of 1 decade, okay, gain is decreasing by 10, right? And that in dB comes out to be 20 dB. So that is why we say if there is a single pole, the gain will fall at the rate of 20 dB per decade. So in my earlier class also I kept on harping upon this. There will be 20 dB per decade. So you got where I got this 20 dB per decade, all of you? Is it okay?
Yes, sir.
Yeah. Okay. So now what about the phase? Now a phase, if you see here, when this is omega is becoming much greater than omega 0, or even if it is going to infinity, this is going to become tan inverse. Okay, omega is going tan inverse infinity. And what is tan inverse infinity? It is 90, right? There is a negative out here, so minus 90. Now, so if I see this plot, okay, this is the gain plot. This is the magnitude of the gain, and this is the phase. So initially it is 0 dB. At cutoff frequency is minus 3 dB. At cutoff frequency it is phase is minus 45, and at a very large frequency, okay, this slope is minus 20 dB per decade, and then this comes and it gets stabilized. This continuously it won't go to a negative, unlike this. Okay, it goes and gets stabilized at minus 90 out here. So these two plots are very critical for you to understand the stability issue. Is this understood by all of you?
Sir, that x-axis is omega, right?
Yes, x-axis is omega.
Why is the gain? Okay, y-axis is
this is gain and this is phase. Okay. I think Momin, you are speaking something. I am not able to hear you. Voltage gain here. Yeah, this voltage gain is from these equations, right? The voltage magnitude is this. So when omega is equal to very less, considering it to be 0, gain will be 1, and if it is 1, it is 20 log 1 is 0, right? So and then when omega is equal to omega 0, this becomes 1 by root 2, which is minus 3 dB. And when omega becomes, and then after that we saw that the slope is minus 20 per dB. So this is going at minus 20 per dB. So initially it is 0, then it is at the cutoff frequency it will be minus 3 dB, and then it will follow a path of minus 20 dB per decade. Is it okay?
The part
Sir.
will be 10 log of something instead of power gain.
It is 20 log gain, right?
I am confused between power gain and voltage gain.
No, this is power gain actually. Okay, this is power gain. Is it okay? 20 log dB is power gain. Okay.
Sir.
Yeah, tell me.
Hello. Sir, it will attain phase of minus 45 at 3 dB, minus
Yes.
3 dB. But
Yes.
In phase method, before 3 dB, minus 3 dB itself, it is attaining minus 45.
Yeah, this is
This graph
minus 3 dB is the magnitude. At that point, it will be minus 45 degree. Okay, and then
Correct.
it will get maximum phase difference from an RC from a single pole will be only 90 degree, minus 90.
Correct, sir.
Okay, yeah. So this is single pole response. Now, if I have two poles, okay. Now, if you have two poles,
So what do you mean by pole, sir?
poles
You're
is
saying single pole.
this is a pole, a RC combination.
Okay.
A low pass filter. Okay, so this will be an pole. So now we have a single pole out here. Okay, this is 45 degree, it is 90. But if I have two poles, okay, one pole and one more pole, there are two RC elements which are forming two different poles. Okay, then what happens is from here it will be minus 20 dB per decade. When it reaches the second pole, it will become minus 40 dB per decade. Okay, so you can do the same analysis which I did here for 2 poles also. So you will get this kind of response. Okay, it will be 40 dB per decade. Okay. Now also if I talk about the phase, here it will be 45 degree, then it will become 90 degree here, and then from 90 it will go to 180 degree. Okay, for 2 poles. Okay, another 90 degree phase shift. So with 2 poles, this is the kind of response which you will get. Is this these 2 plots okay with all of you?
Yes.
Okay. Now if I have 3 poles like this, okay, if I have 3 poles, so first it will here it will come from here to here 20 dB, then 40 dB, then 60 dB. Okay, and from here to here it will have 90 degree phase shift, and then from here to here 180 phase shift, and then from here to here 270. So if you see here, so there is a possibility of 180 degree phase shift, and here also there is a possibility, but this 180 degree phase shift happens at very high frequency, like right when omega is tending towards infinity, then only it will reach 180. Right, in this case, okay, when omega is tending towards infinity, it will be 270, but 180 is can happen within your area of interest. Okay, within the frequency band which you are looking at, 180 degree phase shift can happen. So when you are giving a feedback network, if there are 3 poles, there is a possibility that your signal, by the time it moves through your forward gain, through your feedback system, there is a possibility that the signal gets inverted. Okay, why is the signal getting inverted? Because if it reaches 180 degree phase shift, then the signal gets inverted, and we will reach a situation like this here. If the signal gets inverted, and then again you have a minus sign out here, plus and minus, then you will reach an unstable condition. So this needs to be tested. So wherever there are 3 poles like this, okay, the system is, if you don't take care, it is likely to get into oscillation. Okay, so that is known as, that is why we talked about 1 pole, 2 pole, and 3 pole response. Now, okay, so this I guess we learned. So there are 2 more figure of merits of a circuit. One is known as a gain margin. So what is gain margin is, this is an AB, okay, A beta, that means the total loop gain. Okay, so when the total loop gain, okay, when it is reaching the gain is reaching 0, okay, what is the phase then? So if the phase is not at 180, right, it is less than 180, then that is known as the phase margin. Okay, now so that indicates that the system will be stable. Okay, let me go back to this circuit. Okay, now here suppose there is no signal out here. Okay, here there will be some noise available here. Okay, and this noise will be of the entire frequency spectrum. Okay, so at some particular frequency, if from here to here, and then from here to here, from here to here, okay, the signal is going and coming here and making a 180 degree phase shift, right, and it has also got a positive gain. Okay, from here to here, the gain is more than 1. What happens? Then that will get further amplified here when you add this. So this will continue oscillation. So there are 2 conditions for oscillations to happen. First is, as the signal moves from here to here to it comes back here. Okay, it should make an 180 degree phase shift. Okay, and then also the gain should be more than 1. If the gain is more than 1, even without any input signal, just because if some noise is there, it will go from here to here. It is more than 1 here, again it will get amplified more than 1. So this will start oscillating. Okay, so there are 2 different conditions. One is it has to make an 180 degree phase shift. Okay, the second condition is, okay, that the gain has to be more than 1. If the gain is not more than 1, suppose some noise has got introduced, it will go from here to here, and although it has made 180 degree phase shift, but it has got a gain is less than 1. So now signal available here will be lesser. Again, one more loop it will make, again so the oscillation will slowly die down. Okay, so for oscillations to sustain out here, both the conditions should be met. First, that the loop gain from here to here phase of 180 degree, and also the loop gain should be 1. So unless both these conditions are there, then we say that okay, this system has become unstable. So to give to understand how stable a system is, so that is why we plot this, and we talk about gain margin, and we talk about phase margin. So when AB, okay, when it is 0, okay, so at that time whatever is the phase, okay, now here the phase it has not yet reached 180, okay, so that means this much is the phase margin available. Had it reached 180 degree, then it would have been slight here, right? Any gain more than 0 and phase shift of 180 would have resulted in an oscillation. But in this case, when the gain has reached 0, the phase has not yet reached 180. Okay, there is still some gap there. So that means this is a stable system, and you have a phase margin out here, right? So if this is going to reach 180 before this reaching 0, then it is unstable. Here it is reaching 0, the gain is reaching 0, and it is going to 180 after that only. Okay, so that means, okay, even if when for a higher frequency it is going to make 180 degree phase shift, doesn't matter, because by that time the for that particular, when the signal for that particular frequency at which the signal is making an 180 degree phase shift, the gain is less than 1. Okay, and hence it could be termed as an stable. So at this particular frequency, when gain is 0, when the gain is 0, whatever is the phase difference between 180 minus 180 to this point, okay, that is known as the gain phase margin. So greater the phase margin, better the system is, more stable the system is. Similarly, when it is when the phase gets to 180 degree, okay, the gain is less than 1. Okay, so this is known as the gain margin. So if greater gain margin means that whenever the signal is making an 180 degree for whatever frequency, the gain is much lesser than 1. So it will be more stable. So greater gain margin and greater phase margin indicates that the circuit is more stable. So is the concept of gain margin and phase margin clear to all of you?
Sir, could you please explain this W1 point? Especially, I mean, when gain is 1, and then when it is, I mean, going to the negative direction, so is it negative or it's like less than 1?
Here, is it?
Yes.
No, gain is 1, so in dB it is 0. Right? Gain equal to 1, AB, the loop gain 1, in dB it becomes 0, right? What is dB?
Oh, yes.
20
Understood,
log,
understood.
right? So negative
Understood.
means negative in dB, right? So when the gain is 1, right, then at this particular
Yes.
condition, if when it is slightly more than 1, you can't have a phase margin of 180. If the signal is already 180 degree phase shift, then surely there will be oscillation. So you can't have that, right, for the system to be stable. So this signal, this phase difference, okay, should be, right, less than 180, minus 180, till the time this reaches 0. So that is the measure of stability, and hence this is known as phase margin. Is it okay?
Yes, thank you.
Sir, I have one question.
Hmm.
So when the gain is the highest,
Hmm.
then the phase angle is 0.
Yes.
Is that also not a stable?
Yeah, it is stable here. This entire thing is stable here. Okay. Here also
So
it is stable.
when we call that as not stable,
We will call it non-stable in case the phase margin is 0.
means
Like
if
when
the gain is going negative.
Yeah, when the gain is 0, okay, where gain is 1 or 0 dB, if it has made 180 degree by then it will be stable. or it has made 180 degree before that itself.
No, non-stable. I am saying non-stable.
Yeah,
condition.
for non-stable.
What would that be?
If the phase,
Because means
yeah, I'm drawing that, right? If I have a response like this, right? Now, if you see here, this is making a 180 degree out here, and I have a positive gain here, right?
Okay, for
then
a positive gain 180 degree. Okay.
Yes, then it will become
means there is no
unstable.
phase margin. Okay.
Yeah, there is no phase margin, right? Then this will become an unstable system. Okay, you can't have.
Sir, what now?
Yeah.
So, sir, whenever we are taking 180 degree phase shift signal to the input, then it would be negative feedback.
No, see, we are assuming at the input there will be a subtraction.
So
at the input
A minus
here,
of minus B.
Yeah, then it will become positive. So we want to avoid that.
Okay, we don't want that positive to happen.
Yes, we don't want that positive to happen. Okay.
Sir, I understood this gain margin, phase margin. If it is positive, then the system will be stable. And when you draw in that both were negative, is it possible one of like phase margin is negative and gain margin is positive?
No, it can happen that way also, right? See, I said this phase can come here and it becomes now a 180 out here and it is going like this, right? Now what happens is at 180 degree here, this is it. So I have, now in that case gain margin is this, right? From here, if I draw a vertical line here, this will become, right? No, this is the phase margin, right? So this will become, actually it will be written minus of minus 80 minus whatever is the phase, right? No, sorry. Right, so this has to be from here to here, and I move forward. So this has to be positive, right? So that means it is got a positive phase margin. We call this as a positive phase margin. But if I have this going like this, then this is the line. So if I draw a line out here, right? Then from here to here, then it has got a negative phase margin. Correct? Then this becomes an unstable. You are talking about gain margin. So now suppose 180. This is making an this is making an 180 out here, right? So if I draw a line from here, right? Again here also, this is known as, this will be known as the negative gain margin, right? This is known as a positive gain margin. This is good. So I subtract, okay, this from 0 minus of minus this. So that is defined as the gain margin.
So sir, why negative gain is good?
Because
positive should be good, right?
No. This negative corresponds to a frequency where the signal has made 180 degree phase shift already, right?
Okay.
Then that should be avoided. So that is why below negative
means
is
any negative gain below this, when it has already reached 180 degree, any negative gain after this, what about that? Is that good?
That is better, no, right? Whatever for high frequencies, if it is making 180 degree phase shift, that situation should be avoided. So the gain should be less than 1 on all those cases. Okay.
But it may go to 270 also, right? For example.
Yes.
If
I think I'll show one next diagram. It will be things will be clear here. Like here, like this is a signal. So this will be a situation when it is not made a 180 degree phase shift. Okay. So when you so there will be opposite in phase to each other, okay, and then they will get subtracted, and hence you will get a finite output. But once it has made a 180-degree phase shift or more than that also, doesn't matter. So in that case, what happens is this signal and this signal, they get added up to each other because you are subtracting it. So you may not apply any signal at all. You just interconnect this. If you interconnect this in the frequency band, if I go here, right, there will be noise in all the frequencies, right? There will be noise always, some small amount of noise across all the band. You can't avoid that. That will be there in the atmosphere in these devices. So a small noise, what would happen? It will come here, it will come here, it will come here. Okay, 180-degree phase shift again, and the gain is more than 1, so it will get amplified here. Again, second loop it will make, it will get further amplified here, and it will keep getting amplified with each passing loop, and finally this transistor will generate a square wave. Correct? It will keep getting amplified that way till it gets saturation. Is it okay with all of you? Okay, so this is how stability is defined. Okay. Now let's take one example out here, right? This is one. Now I have put one C out here. So this has become an RC. This has become RC. So these are all three dominant poles of these three. So there are three stages. I want to give a feedback like this. I want to give a feedback like this from here to here. So I don't want it to be unstable also. So what would be the case? Now if you see here, since all the values are same, RC, RC1, RD and C1 we have used, all the three poles coincide into one particular place, and then from here it is making minus 60 dB per decade. Okay. So here it is starting at 0. And at 1 by RC, okay, it will not be minus 45 because there are three poles together here. So minus 45 into 3 will be minus 135, and at very high frequency, because there are a total three poles, it will go to minus 270. Is these two graphs clear to all of you? Anybody has got a doubt?
The last one, can you explain again?
There are three
135 to 70, that one.
See, the maximum it can go, since it is three poles, is 270. Okay,
Correct, sir.
and at that resonant frequency, okay, for one pole it is 45, but since there are three poles, now it will be 3 into 45.
Okay.
So minus 135. Okay, so that will be the phase difference. Now if you see here at minus 180 degree here, okay, when this signal is going minus 180, I want this gain to be less than 1 for this to be stable. Okay, isn't it? Right?
Yes, sir. Yes, sir.
So at 1 by RC, omega is equal to 1 by RC, that is 1 by in fact since it is 3 RC, okay, I have minus 135. Then after that, okay, that is after that, some at 10 it will be 270. Somewhere in between omega and 10 omega p, okay, it will have 180 degree also. Omega p will be 1 by 3 RC, right? At 10 omega, see, it will 1 decade, it will come up to run. So somewhere there could be a chance of this getting to 180 degree. So for that particular, so you have to ensure that, okay, the gain is such that, okay, so it has to be less than 1. So that is done here. So this is the gain, GM RD into RD cube, right? Is this gain equation clear? Because there are three stages, 1, 2, 3 stages, right? And it is not just GMRD, because there is a capacitor also. So you have that on the denominator, you have a pole. So this is the gain, right? So this is the frequency. So for 180, okay, so this is minus 3 tan inverse omega by omega p. So omega px, okay, where for 180, so for 180, I have to find out for 180 what is the frequency. So I put an this as minus an so tan inverse this is 180. So tan inverse omega by omega p will be 60, or this, for which this is the frequency at which the phase will be, the feedback phase will be 180 root 3 omega p, right? And this is the gain. So if I put these values omega root 3 p out here, right, px as root 3 omega p, I will get the value of GMRD to be less than 2. So as long as I use a gain GMRD is less than 2, this circuit will be stable. If I use GMRD is greater than 2, then this will become unstable. Is this okay? Analysis, is it understood by all of you? Anybody has got a doubt? You can ask me.
Yeah. Sir, here omega p is nothing but omega 0, right? That is 1 by RD, you see.
Omega 0 is omega p, okay, and that is 1 by 3 RC actually, right, because there are 3 poles out here. Single pole, it would have been RC. Yeah? Oh, no, it will be just RC, sorry, yeah.
Because that RC was given in the graph also there above. Because at 1 by RD, you see the phase was minus 135.
Yeah, correct.
But that omega p is 1 by RC.
1 by RC. Yeah, my mistake. 1 by RC. Phase will be minus 3. Okay? Is it okay?
Sir, closed loop gain is 1 upon 1 plus A beta. So here you have written H of S. So can you just explain, like here A is GMRD and this omega term is related to the beta feedback network?
See, actually what we are doing out here is, this is a kind of this output is straight away fed here. We are talking about giving a feedback directly out here, right? So a signal from here to here, okay, we are seeing that it is going to make a 180-degree phase shift. At that time, what would be the gain? That is what we are trying to compute it.
So here beta, what we have considered in the gain equation?
Beta is 1.
Beta is 1. So, sir, like how to write this equation? I don't understand that thing. Like gain equation, H of S.
This one, we are talking about the in this case we are talking about the open loop gain.
Okay, this is open loop gain.
Yes. Right.
So yeah, sir.
Because alpha beta we are trying to find out a condition of 1 here. So beta is 1 here.
Okay. Right. So sir, for any
we are trying to find out a condition
this?
where alpha beta is equal to 1, so that there is no instability there.
Okay. So sir, for any circuit, how to write this gain equation that you have written for this circuit?
This one, is it?
Yes.
This is like a normal GM into, right? What is the this thing, gain of this particular stage? It is equal to GM into RD parallel to C1, right? Right? GM into RD into 1 by C j omega divided by RD plus 1 by C j omega, right? So you simplify it, it would come to this.
Okay.
GM by 1 plus S by S, right? If you replace this j omega by S, so that is what has been done. Okay.
So are we saying that phase crossover occurs that equal to 60 degree?
Because we are talking about 180-degree phase shift, there is already a -3 here. So So because of this cube out here, right? So we are talking about just omega by omega p should be 60, because there are 3 poles out here, right? From here to here it will make 60, from here to here again 60, here to here another 60, because there are 3 poles. Okay, is it okay?
Sir, how do we plot that plot the frequency response of the, how do we do that?
This one?
No, in the next slide.
Here?
Yeah, plot the frequency response of the circuit and determine the condition for stability.
No, we need to write the gain equation. Okay?
What do we need to plot here actually?
No, we have to find out when the signal moves from place from here to here and come back, what would be the total phase shift. So we have to write the transfer function, right? We have to find AB, the gain AB.
A beta, okay.
Right? Here beta is equal to 1 in this particular case. So because we are saying we want to directly couple this, so we need to find out A, right? So A is one gain multiplied by second gain and multiplied by the third gain, right? So a single gain is GM divided by 1 plus S by SP. Okay, that I think we did that when we did the frequency response lesson, right? So same right? Frequency response we did that, right? The same thing for when we identify the poles and then write in the denominator those poles. So the single pole, so it will be S divided by, now multiply again 3 times. So this becomes cube, this becomes cube. Okay.
Sir, in the previous slide you have written omega equals to 1 upon 3 RC. So can you please remove that? Yeah. Otherwise we will take it wrong.
No, okay. This is RC.
Sir, how that root 3 comes, sir? Like it is tan 60 is something related to that?
Yes. Root 3 is tan 1 by 3, right?
Okay, tan 60 is.
Yes. Right? 1 by root 3, right? Tan inverse 1. No. Where did this root 3 come, right? This
no, sir. No, sir. Like the root 3, how it comes?
Root 3. Right? Tan inverse omega by omega is 60, right? This is 180. This entire thing is minus 180. Right? So tan inverse omega by omega p will be 60, right?
Yes, sir.
This. Right? And tan 60 is what? Root 3, right?
Root 3.
Yeah.
Okay, then how, where that 3 wins, sir?
Which 3? That
3.
From 180, that 3 has got divided and we reach 60, right? This is 180, right? For the loop gain to become 180, we have this, when it signal goes from here to here, here to here, here to here, 180 degree phase shift, right? So that is minus 3 into this much is 180. This is equal to minus 180, right? So this 3, this minus goes and 180, this becomes 60, right?
Okay.
Right? From that 60 again, you write. So this is the condition. Right?
Sir, how the GMRD is less than 2?
GMRD. So that is the condition. Because here, if you see here, okay, here, from here what you get, omega px is equal to root 3 times. So you put root 3 out here, right?
Yes, sir.
So root 3 square, how much will it be? I think 3 plus 1, 4 and cube. So that has to be less than 1, right? So from there it has come.
Sir, actually, I'm so sorry. That minus 3 into 60, you said it is minus 180. Okay. Then how we reach root 3 into omega p?
Right? This is a tan inverse of omega. Tan inverse, what is tan inverse 60?
So here, in the place of tan inverse omega by omega p, we are substituting as 60, then it will come minus 3 into 60 is minus 180 will get what you said.
No, no. Did you get this equation? Tan inverse omega by omega p is equal to 60.
Yes, sir.
So omega by omega p will be tan 60, right?
Tan 60 is root 3, I think.
Yes.
In terms of, yeah.
So W equal to root 3 into.
So W will be root 3 WP.
Okay, okay. Okay, we are simplifying only for this.
Yes.
Okay.
Okay. Here, again, from that value, we are putting it here. Okay. So W. So this will become 3 plus 1, 4. Square root will become so that we are taking it here. So GMRD, is it okay from here to here?
Sir, one question, like why we are computing the gain should be less than 1 here?
Because when the phase is 180 degree, okay, when for this frequency the phase is making 180, right, and if the system has to be stable, for that condition the gain has to be less than 1, otherwise it will not be stable. If it is more than, right, for this frequency, for this particular frequency, okay, the phase difference is 180 degree, right, and at this particular condition, if the gain is more than 1, then any amount of noise which is available at that particular frequency, when you are giving a feedback, that will become an unstable system. It will, without any input, that will keep getting amplified. So we are ensuring that for for that particular frequency and above, the gain is less than 1.
Okay, to get a stable. Yeah, got it.
Yeah.
Thank you.
Okay. And somebody had this query on GMRD. Is it clear? Here you put root 3. What happens if I put root 3 here? This will become, I think, under root of 4, right?
Denominator.
Right? Then this 3 and this 3 will go. Under root of 4 is 2. You take it here, so GMRD will come less than 2. Is this thing clear to all of you? Where did this come from? Less than 2?
Yes, sir.
Yeah. Okay. Yeah. So this is the condition. So can somebody say, will this system will be unstable at any time if you give a feedback like this? Can it be unstable?
It's only one pole.
Yeah, there is only pole. So maximum 90 degree phase shift only it can happen. So this will never oscillate. Okay, this will always be stable. Okay, so this cannot be unstable, right? So many a times what we do is, okay, to make the system stable, we add one compensation capacitance, okay, pole compensation, so that the gain rolls off early here. Instead of like this, you make a dominant pole here, right, so that it goes early and it comes to 0 before the phase comes to 180 degree. So here it is coming to 180 degree out here. So in this case, you can see the earlier graph, okay, which was out here, right? And let me remove the things which I have put. Right, the dotted one is without the compensation. When it is reaching 180, the gain is more than 1. You can see here, right? Here. So it is an unstable condition. So if this is to happen, what I can do is I can add one more dominant pole here. So by adding one more dominant pole here, this is going coming to a 0 out here. Okay, by that time, okay, because this is a dominant pole, so single pole. So by the time it is coming to 0, the phase is just 90 there, okay, or it is not yet reached 180. So that means this can become stable, because single pole cannot oscillate, right? And I am making that single pole very, very dominant. That means so I am restricting the bandwidth, okay, of the circuit for stability, and since the bandwidth is reduced, the gain will keep reducing as the frequency moves, and it will come to 0. And since that is a dominant pole in this region, you will have only 90 degree phase shift. So it will not reach 180 degree. So this is known as a frequency compensation. Is this concept okay with all of you? Yeah, Chinna, Sunil, is it okay?
Sir, can you please explain the compensated design?
Okay. The compensating is by introducing one more pole out here. Okay, I am making this gain rapidly come to 0 even before the phase comes to minus 180 degree. Okay, so I am so the phase comes to 180 degree when you have this condition of 3 poles, right? But I am making one pole. I am making it like function like a single pole by making a very dominant pole. That is, I am pulling this pole much ahead. So this will start rolling down and it will reach 0. Okay, 0 dB. And since this is a dominant pole, single pole, the phase difference will be around 90 only. That way I am making this thing stable. Is it okay now?
Yes, sir.
Okay.
Sir, what do you mean by dominant pole?
Dominant pole means the position on the frequency domain, it is closer to the origin, one which is closer, because that now defines the overall gain. That is the one which has got more effect on the gain.
So from the original design, we have removed the previous components, RC components.
No.
And we are replacing it with the only one.
I have added one more capacitance. I'll show you the circuit diagram. Okay.
Okay.
Now this is one amplifier. This is second amplifier out here, right? So this was the original. Okay. There were 3 poles out here. Suppose. Okay. There is one node here, one node here. So now what I am doing, I am putting one more capacitance out here, additional capacitance. Okay, which is a dominant capacitance. So now if you see here, now this is how this additional capacitance which I have inserted here. Otherwise at node A there will be one RC, at this node there will be RC, at this node there will be RC. Okay, there are at each of these nodes there is, and here also there will be an RC. So there are all different poles are available out here. But I am putting a very large capacitance here, right? And hence from here itself it will start. Because high frequency will start getting grounded here, right? Because of this capacitance which is put here. So this RC. So this RC. So obviously the bandwidth gets limited, but stability will increase. Is it okay with all of you?
So sir, this capacitance is added by adding a high, like more width transistor.
No.
A transistor.
No. This is a MOS capacitance which is added. Normal capacitance you pick up from the technology.
But on fabrication side, sir, we are adding we are manufacturing transistor only.
No. We can take resistances and capacitances also. Okay, it's possible, right? Capacitances are fabricated like that only. The way a gate is fabricated, right? There will be a metal layer, there will be an insulator, and there will be a channel. And in the channel towards the end, there will be some high doping, and they will take out the terminals. So you will fabricate capacitances also like this. Okay, metal separated by insulator, and then you will have a highly doped channel here. So capacitances are very common. Okay, capacitance resistances are also fabricated.
Okay, sir.
Okay, so this is not an intrinsic capacitance, mind you. This is an extra capacitance which we are going to put it here to get this response. Okay. Now, if I have to find out this RC value, okay, what is the resistance as seen into this node? Okay, it will be M, like this we saw, right? GM R0 R2 parallel to this. So this capacitance along with the resistances seen at this particular node. So this is the dominant pole now. Okay, there will be one pole out here at node A, right? And here, if you see here, the stray capacitances, this CA is the stray capacitance, not the external capacitance. Capacitances of these devices, okay, along with the GM2. If you see, whatever is the right. If you see from top to bottom here, this is a high resistance, but from bottom to top, it is a low resistance. So that becomes so you can neglect this resistance of M1. So GM2 CA, is this the top value understood by all of you? Why is it is GM2 by CA? 1 by Gm is the resistance as seen into M2, right? Right? Omega is equal to 1 by RC, right? So, C is the net capacitance at this node because of M1 and M2, right? And the resistance at this node, if you look towards bottom, it will be R01, okay? And if you look towards the top, it will be 1 by Gm2. So, 1 by Gm2 will be much lesser. So, this is the first pole, WPA. Similarly, here there will be a capacitance, and here on top and bottom, if you see out here, it will be R05 and R06 in parallel. So, this is the one more pole which you see. Now, this pole we are talking about, okay, this is the capacitance which we have added, okay, which is known as C compensation, right? And then when you look the resistances onto the top and to the bottom, this will be the resistances which will come in parallel. So, this is how we make this particular system stable, okay. If it is an open loop, there is no issue, but whenever but open loop, we saw that in analog, generally we use it in a feedback path, right. So, in those cases, to avoid to avoid oscillations, then that is the case. Then we put these kind of capacitances in between to make it stable. Is it okay with all of you till here?
Sir, can you please explain that omega PA? How come it is GM2? I did not get that.
Okay.
Sir, can we take 5 minutes break after this question?
Yeah. Okay. So omega PA is the what is the capacitance out here? I am writing it as CA, capacitance at the node at this A. Okay. That could be because of the drain capacitance of M1 and the source capacitance of M2. Okay. So, that is CA. And what is the resistance at this node? If you look from here to the top, it will be 1 by Gm. And if you look towards the bottom, it will be R0, because here it is constant bias. When you're like we learned, right, when we look into the source of an NMOS, okay, into the source, it will be 1 by Gm, and when we look from the top, here the gate source voltage is fixed, so it will act like a constant current source, whereas here it will not act like a constant current source, because gate source there will be a modulation of this voltage here. So, and hence the impedance offered will be lower. So, 1 by Gm, it is 1 by Gm. So, 1 by C into R is 1 by Gm. So, that Gm goes on to the top, Gm2. Is this okay now?
Yes, sir. Thanks.
Okay. So, this is there. This output at this particular node, okay, this will be WP Bout 1 by R05 parallel to, because when you look here, it is a constant current source. When you look into the bottom also, it is constant current source, right? Because this is PMOS and this is NMOS. So, R05 parallel to R06. So, that is the second pole. But we want to make a dominant pole out here, right? So, this is the capacitance. Is it okay? Yeah? Okay. So, I think there is only one more slide on compensation, and then we will take a break and we will talk about oscillators next. Okay. Now here in this case, you have to use a big capacitance, so that could take some area. Okay. So, to have instead of connecting that capacitance to ground, if you connect it like this out here, right, as the signal is moving from here to here, okay, there is a voltage gain, because this is a first stage amplifier, this is second stage amplifier. Okay. So, what is this? This is PMOS, right? This is a current load. This is the load for the PMOS, right? So, from here to here, it is what? There is a signal gain when it is from here to here. So, this is, you can write it as C equivalent, and this is a Miller capacitance actually, right? So, you can multiply this with the gain of this stage. Okay, the gain of this stage will be GM5 into approximately GM5 into R05 parallel to. So, although you are adding a smaller capacitance here, the net effect will be gain of this amplifier into that capacitance, right? So, by putting a small capacitance here, effectively you are putting a very large capacitance, Okay, so this is known as Miller capacitance, and this is very much used in all the op amp designs. If you remember, when we discussed about op amp design also, if you go back to your classes, there was one capacitor which was connected there. So then I told we'll talk about this capacitor later on. So this is that you can open up that and you will see there was a capacitor which was connected there, that is known as the Miller compensation. Is this Miller compensation clear to all of you? Why we have done? The thing is, we can use a smaller capacitance and achieve a higher, we can make an dominant pole here.
Sorry, smaller capacitance means?
The value of the capacitance will be small and hence the area occupied by that will be small.
Yes, but we are putting less value, then gain is not getting good. If we are putting
no. This capacitance is not making any difference. When I make an equivalent of this, okay, because like if you remember in the CS amplifier, this capacitance, right? This capacitance actually gets multiplied by the gain, right? Equivalent circuit, right? Here it is PMOS, okay? So this capacitance from here to here there is a gain. Now this is the equivalent. Now this equivalent capacitance is actually C into the gain. Gain is this much. If I neglect 1 plus. Understood?
Yes,
Jason, have you got it?
Yes, sir. Yes, yes, right? Sir. While putting that the assignment also there we need to put one capacitance.
Okay.
Capacitor. So if we are putting less value, then it was not coming gain proper. If we are putting good value, link farad something, it is 10 to the power 15 minus 15. Okay. Then we are getting good gain.
Yeah. Suppose 100 femtofarad capacitance is required here. Now, if I am connecting it like this, okay, and I am already having a gain of 10 in this stage, then I can put a 10 femto only here. Okay, because equivalent will be like that. Because so I can use a smaller capacitance there. So that will not take that much of area.
Got it.
Okay, so that is what.
The example, this one, So here we considered omega PA, omega PB, and omega P out, right?
Yes.
So why those nodes are considered? Means, let's say some problem is given. How to pick the nodes is the question, sir.
In the signal path, you will have to see. Okay. As the signal is moving, it's moving from here to here.
Correct.
Right? The signal is moving from here to here, so I have one node.
Correct.
The signal is moving from here to here, so I have a second node P out here. Okay, this node I won't take because this is actually this entire thing is an effective resistance for me.
Exactly. Correct.
So then I have this node here, and then when the signal is coming from to here, I have one more node.
Correct.
Okay. Clear. So I have to see my signal path. So wherever there is an RC combinations available there, so I have to look after that. Okay.
Sure. Thanks.
Okay.
Clear.
So now what is oscillator? Okay, oscillator is nothing but you give a power supply and you don't give any input signal. It should give me either a sinusoidal signal or a square signal of its own. Okay, so that is known as oscillator. Okay, it is basically a frequency generator. So whatever frequency or a clock generator. Okay, they all come under oscillators. So how do the oscillators work? Now here we want it to we don't want stability here. Okay, so suppose this is an input signal which is given here. It is making an 180 degree phase shift out here, and you are giving subtracting these two, so this will get added up. So if it is getting added up, it will given in the next cycle it will give a bigger signal out here. But even if this is not there, because of some noise for that particular frequency where it meets this criteria of gain is equal to 1 and phase is equal to 180 degree, this will give me an output. Okay, so that is known as so we have to target these two conditions and ensure that for our desired frequency the gain should be slightly more than 1. Why I am saying slightly more than 1? Then because then if the gain is very high, this will keep very far at a fast rate. It will keep increasing, and it will reach a saturation where I'll start getting square wave. Okay, this will go into saturation. But square waves also is used in many applications. But if you are interested in an sinusoidal signal, then obviously you cannot make exactly one. If it is slightly less than one, then this oscillation will slowly die off. So you just try and keep slightly more than one. Okay, one is an exact condition. So that is what an oscillator is all about. So how to get that? So obviously minimum 3 poles is required. So I have this one, I have this one, this one. I am giving an feedback here, right? So in the earlier case, we said for stability, gain should be less than 2. Here I am going to say the gain A0, that is GM into RD. GMRD should be equal to 2 in this case, okay, or 2.01 or 2.1, something like that, for the oscillations to sustain. So if you connect something like out here, right, the frequency will be given by omega d by like omega is equal to 1 by RD into CL, right? So that frequency. So that particular frequency output signal I can see here without giving any input. You see there is no input given here, right? And I don't have to start this also, because there will be some noise there in the circuit which will trigger this circuit. Okay, in all practical circuits, okay, some noise will trigger this circuit. Okay, because initially some oscillation has to start. Then as it keeps moving, it will keep getting amplified. So our desired frequency, we can assume that noise of that particular frequency will be available. Okay, say I am designing this for 100 kilohertz. So 100 kilohertz noise will be there. That will get amplified and keep getting. All other frequencies, it will not get amplified. Okay, so either the gain will be less than 1, or if the gain will be more, the phase will be less. So all those other noise components will be suppressed. Only this condition which is meeting this particular condition, okay, where the phase is 180 and gain is 1. So that particular, for that particular condition, a loop will be formed, and I will get a desired sinusoidal signal at the output. Okay, I'll show you some simulation also towards the end of this class. So this is how you design this is one oscillator design. Okay, so if you are asked to design an oscillator for a particular frequency, so you can do this. Okay, so these are the conditions which needs to be met. Okay, one is GMRD. Okay, the other one is the desired frequency. Okay, so that you can do this. Okay,
sir. Hello.
Yeah.
Sir, how do we get sinusoidal, because noise is not exactly sine wave? So how that is formed from the noise itself?
No. When I talk about frequency, okay, so this is the frequency, right? This, when I talk about this particular frequency, okay, which is meeting that criteria, that is one particular frequency, and that is sinusoidal. We know that all other waveforms are actually like if I talk about a square signal, it is actually sum of many signals, right? But this only one particular condition is met, that means it is a sinusoidal signal, only one frequency, right? That's what Fourier series says, right? All waveforms, signal waveforms are actually made up of basic fundamental frequencies, right? So which is sinusoidal or cosine in nature.
Okay. So
even the noise can be called as a sum of many cosine of various frequencies. Okay, so from there, that particular frequency of interest, that particular frequency will be picked up and amplified, and it will start oscillating from there. Okay, so this is one oscillator. So this is a second type of oscillators are LC oscillator. Yeah, tell me. Yeah.
Hello. Sir, one query. In the previous slide, you mentioned that we have to design the oscillator for one particular frequency, right? That frequency is actually that omega 0 where it's the pole starts rolling off.
Yes.
Okay. So that will be 1 by RC.
Yes.
1 by RC into CL.
Yes. Okay. Yeah. So now see LC. This is known as LC oscillator. This is an inductor and a capacitor which are taken into parallel. Actually, all inductors, when you make it on a VLSI chip or discrete also, it will always have a series resistance. Okay, and this circuit is equivalent to this circuit, actually, this circuit. Okay, where the value of RP will be given like this. How did I reach from here to here? If I write the impedance of this, right? If I calculate the impedance of this, and if I calculate the impedance of this, right? Write L and then we try to equate a term wise that resistance value. So you will get this. Okay. So this is an equivalent of this circuit. Is it okay with all of you? This and this circuits are equivalent. Okay. If you try to find out the total impedance of this and total impedance of this, it will come out to be same. Only thing is this RS value will now be represented by L omega square divided by RS. Okay. So if I write just a pure mathematical equation of try to find the impedance between these two nodes and these two, you will get the same thing. Okay. You can do this and have a look. Okay. So now you will find that now why I have drawn this out here, because parallel, this is what physically I want to implement. This is actually, it will get implemented it like this, because when I make an inductor, there will be a series resistance, and just for analysis purpose, okay, I am making an equivalent circuit. An equivalent circuit of this is this. Okay, the third circuit. Okay, this one. So now if you see here, when I change omega from here to here, okay, for omega is equal to omega 1, okay, which is known as the resonant frequency, the impedance will be maximum. Okay, and then for frequencies below that also the impedance will be lower, and above also the impedance will be lower. At this particular resonant frequency, right? At this particular frequency, this L and this C will get cancelled with each other. Okay, so that omega will be 1 by root LC, right? For that particular frequency, they will get cancelled each other, and this impedance, this will be RP, right? For all above that, this will be the equation 1 by Z is equal to, for all, for general, for any frequency. So now if you see from here, from this equation, okay, if you equate this, okay, if you equate this here, you will get omega square, and then LC, right, and then you take into the denominator, omega is equal to root of LC. In that case, this will get cancelled. So 1 by R, 1 by Z is 1 by R, Z is equal to R. So at this particular frequency, this circuit will offer maximum impedance. Okay, because the whatever effect is of the inductor will get cancelled by the capacitor. Okay, they will cancel each other. So this will be there. In all other cases, they will not cancel each other. So you will have lesser impedance. Okay, is it okay with all of you?
Sir, what is RP here?
RP is an, if I draw an equivalent circuit of this, it will be like this. RP means resistance in parallel. RS means resistance in series. Okay, so the value of RP will be given by this equation. Is it okay?
Sir, how we have find this RP? Is there any?
Yeah, you can do a simple derivation of it. Okay, you find the impedance of this. Okay, you write an impedance equation of this, right? And then wherever there is no omega, and you write an equivalent impedance of this. And if you equate the terms which doesn't have omega here and here, right? You will get this value. Is it okay? Okay. The one which doesn't have a frequency dependent component.
Okay.
So you equate these two, you will get the value of R like this.
So when the capacitor and inductor impedance cancels out, the impedance should be minimum, right? Why we are saying maximum?
Here? No. See, they will get cancelled out each other, and there will be no the current which is flowing here, okay, will get cancelled by the current which is flowing here, right? And in that case, least current will flow. But if they are not getting cancelled, okay, properly, then there will be a net current which will be more than the current in during the resonance. So the impedance will be lesser. Now that can be out of phase or leading or lagging. That depends on which is the capacitor stronger or the inductor stronger from this equation. Is it okay? Is it okay? Is it okay?
Sir, here in equation, it should be omega L minus 1 upon omega C, or is it 1 upon omega L?
Here?
Here in the denominator, C should come. Like normally we write in 1 by omega C.
No, this is already 1 by Z. So that is why. E max by admittance we are writing. That's why it's coming like this. Okay. Now if you see, now I have one amplifier. Okay, this is driving one more amplifier out here, and I am giving a feedback like this. Okay. Now because this is an so at that particular resonant frequency, okay, so it will have a highest impedance. So the gain from here to here, it will have greater than 1 only for that particular resonant frequency. For all other frequencies, okay, the gain will be less than 1. So you have to adjust your values of you can adjust the values in such a manner, okay, the values of RP, so that this gain multiplied by this gain is 1 out here, and here you will get from here to here it is 180 degree phase shift. From here to here it is again 180 phase shift, and you are adding it. Okay, so that means from here to here the signal can do an oscillation, right? So 180 degree, this is a CS amplifier, right? So it will be 180 phase shift plus 180 phase shift. So two 180 phase shifts you are giving it back here, feedback. Okay, since you are adding it here, that is why you are taking two 180 because you are giving the same signal directly here. So you have this signal going like this, so this will start oscillating, right? And at oscillation frequencies, and this will get cancelled each other. So the gain of the first stage will be GM into RP. The gain of the second stage will be GM into RP again. So the total gain will be GM into RP square. And if you are ensuring that this is greater than 1, then this will oscillate. Okay, so this is how you can design an oscillator. Is it okay with all of you till here?
Sir, from output to input, the phase shift should be like 360 or 0 degree.
Yes.
Like it should not be 180.
No, actually, see what we are when we were talking about these circuits, there was an subtraction here. Okay, we are telling it's a difference amplifier. Okay, but if I am using a single-ended amplifier, then obviously I can't do any subtraction here. I am adding it here only. So entire 360 is taken care of here. From here to here, it has to be right because there is no subtraction here. So that 180, another 180 of subtraction also you have to take care in the loop.
Correct.
Okay.
So each amplifier will give 180 degree phase shift. So total will be 360.
Total will be 360. So this particular minus is what making another 180 degree phase shift. That also needs to be taken care of in the loop in this particular circuit. Correct? It's a single-ended amplifier. Okay. So this is one kind of oscillator which you can make. This is an RC oscillator. You have an op amp and you are giving a signal here. So you have a 1 CR, 1 CR, 1 CR, right? Now if you write the equation of Vx with respect to V out, it will be R divided by 1 plus CR, right? So again, we know that one pole cannot give 180, so there are 3 poles which will be required. So this is the equation, right? Now for this to be so the resonant frequency will come as this one, right? If you equate this to 180 degree, this will come to 3 RC, and then the gain of again this amplifier has to be minimum 2. Okay, this is the same RC. So this is known as phase shift. So RC we are doing. This is known as phase shift oscillator, and 3 sets will be required. At least 3 poles you have to introduce here. So this is another kind of oscillator.
So that means each one will have the phase shift of 60 degrees.
Yes, you have. So for different frequencies it will have different, but for the resonant frequency it will have 60. So that particular frequency will get selected and get amplified, and it will start oscillating. Okay. What is not shown out here is this amplifier gain. Okay, this amplifier gain has to be 2. So unless that is there, okay, it will not oscillate. Okay, so these conditions are. So this is okay. So these are another 2 kinds of oscillators. This is known as Colpitts and this is known as Wien-bridge oscillator. Okay, so these derivations are also pretty simple. So I would expect all of you to go through. There's a lot of literature available on these. These are also widely used. If you see here, okay, these are all small oscillators as compared to all these oscillators. So this is a single MOSFET amplifier, right? Oscillator, just single. So how this phase shift is done out here. So you see there is no input signal for all these things. Okay, they will start oscillating. So just try to see the derivations for these things. Okay, this RF1 and RF2 have been given to adjust the gain of this amplifier. Okay, so what should be the value of RF1? What should be the value of RF2? What is these R1 C1 R2 C2? Okay, how to design an op-amp based amplifier for various frequencies. Okay, so that design of an oscillator. So basically, if you are working in an industry and if there is a requirement of generating some sinusoidal signal, you should be able to do that either using an op-amp or using a transistor. So this as a home assignment, just go through these oscillators also and try to do some simulation and try to get some results. Okay, so these are some of the conditions which needs. If you don't adhere to these 2 conditions, it will not oscillate. Okay, so you can try it out so that you are unless you do it yourself and try to find out what are the mistakes which you are doing, you will not learn. Okay, but I will nevertheless show you one small simulation. See. Okay, so now if you see what I have done it here, this is an inverting amplifier. I have used this 10K and 550K to adjust the gain of the amplifier, and then I have used this RC network to give the phase shift. So you see there is only power supply. I have given a minus 15 here, plus 15 here, and an op amp, and RC here, and R5 and R2 out here are to adjust the gain of this amplifier. Now if I simulate it and if I try to plot the output, now probably why is this signal continuously increasing? Can anybody say what could be the reason?
It's stabilizing.
No, it's continuously increasing, I guess.
Sir, due to positive feedback, it is increasing, and
yeah,
after some time it will get.
Yeah, it will get into saturation. Probably I have given this value too high. Okay, so let me further increase and see what happens. Okay, 10K, 1000K, right? So you see, I start getting it is getting into the saturation. The gain is very high. Okay, so probably you see now
we can limit it to 2.
Yeah, so I had put 550 initially, I guess. So let me put 500. Okay. Right. Now what is happening? the oscillation is
It is
slowly
dying down.
dying down, right? So you have to, so this is how when you do your simulation, so you have to set these conditions. So these, unless these conditions are met, you won't get an oscillation. So 520 is probably not adequate. So 525. So these you see it will slowly it is better now. 530. So it will sustain oscillation. Okay. I have to
45 you put.
Yeah.
545.
Yeah, I think this is okay. So you have to set like that, right? So the gain is one important parameter. So this is how you design frequencies and oscillators, right? So you can do that. Now, if you want to change the frequency of oscillation, okay, now I can change these values of like let me put it as 18K. So obviously the frequency is reduced, but then accordingly I might have to also do the adjustment out here also. The signal. See, now I'm getting a sinusoidal. I'll have to. Right. Okay, I'm at still I have to reduce. Yeah, you see slowly things are improving, right? So this is with an I have picked up an op amp. You can try it out with an transistor. Okay, so in one go you may not get the results. So you have to you should know what is happening. Okay, the RC the oscillation frequency will be decided. Then you have to ensure that the gain. So initially you can target an high gain so that at least you see a square output. Okay, then finally you can fine tune it. So because otherwise if you start with a low gain, suppose, so you will be getting a straight line like this only. So you will not come to know what mistake you are doing, right? So it is always better I start with a big value, something like this. Okay, and I do it, and then okay, now I know I am getting output plus 15 to minus 15. Then I can I can see the frequency also. Otherwise, I won't even come to know now what is the problem, whether there is a free. So when you are designing, when you are doing a simulation, it is first set the gain very high and get some results. Okay, it will be in the form of a square wave, and then slowly then you will also see the in the square wave itself you can see the frequency also. So once you set those frequency and then slowly you can reduce the gain and get the desired oscillator.